Okay, let's start a new chapter today about bonding in coordination compounds. So first of all, let us think about what, in general terms, a good bonding theory should be able to do. Can you think about what would make a bonding theory a good bonding theory? Do you have any suggestions?
I think in general, one thing that a good theory overall should be able to do is explain a concept with as few exceptions as possible.
Correct. So a good theory in general would be able to explain a lot, making only a very few simple plausible assumptions. Okay, so it could explain a lot of experimental phenomena, and it would be able to predict correctly a number of experimental phenomena. So now if we apply these very general considerations to bonding theory, then what would be the experimental phenomena the bonding theory should be able to explain or predict?
Electronic interactions or interactions with electrons between atoms.
Yeah, so that would produce the bonds, right? So it should explain the number of the bonds, but also it should explain then the shapes of the respective molecules. So that's one important parameter. Another one is that it should be able to explain the magnetism of compounds, okay, in particular diamagnetism and paramagnetism, how many unpaired electrons we have, and if we do not have any unpaired electrons in the case of diamagnetism. It should also explain the reactivity of compounds and the stability of the respective compounds, and it should also be able to explain the optoelectronic properties of the compound. So it should explain if a compound absorbs light, and then what kind of light is being absorbed or emitted respectively. All right, so let's just sum this up. So it should explain and predict, okay, the number of bonds and the shapes. That should be an O here. It should explain the magnetism, whether it's diamagnetism or paramagnetism. It should explain the stability and the reactivity of the complexes, and it should explain the optical properties via electron transitions. Okay, if it can all, the bonding theory can all predict all these things and explain all these things very well, then we would say, well, we have a good bonding theory. Okay, so now what bonding theories will work best for coordination compounds? So there are actually three bonding theories that are applied to coordination chemistry. So they work not all equally well, and but they're also not all equally uncomplicated. So as a trend, the less complicated ones work less well, and the more complicated ones work better, but they're more difficult to handle because they're more complicated. So the first theory, which is used in coordination chemistry, is valence bond theory. So you know valence bond theory from main group chemistry, where it works extremely well. So in this view, we have actually two half-filled orbitals, valence orbitals, that, well, overlap to make a covalent bond. Okay, So that concept is widely applied in, well, organic chemistry, for example, but also in other main group chemistries. Okay, so valence bond theory explains a covalent bond, okay, by the orbital overlap of two half-filled valence orbitals, whereby then the two electrons are being shared, okay, between the two partners. Okay, so now in coordination chemistry, we say, well, we also have covalent bonds, but we consider our covalent bonds to be dative bonds, where we have donor-acceptor interactions and one partner contributes 2 electrons, whereas the other partner contributes none. So how would we then define valence bond theory for coordination chemistry? Well, there's not much that we would need to change. Okay, we'd say, well, we have here this empty orbital of our acceptor of our Lewis acid, and here we have the full orbital of our Lewis base. Okay, well, we let this overlap, and well, we again create a covalent bond in which the 2 electrons would be shared between the 2 partners, but because now 2 electrons came from one partner and 0 electrons came from the other, that would be a dative coordinative covalent bond. Okay, so now how well does valence bond theory work? It works extremely well for organic chemistry and the main group elements. However, it does not work overly well for coordination chemistry. So it can explain certain shapes of complexes, but not all shapes. And in some cases, it can also explain magnetism, but in other cases, it can't, and we'll see why. By nature, valence bond theory can never explain the optical spectra because it just cannot, it does not work with electron transitions. Okay, and that's the case for both main group chemistry as well as coordination chemistry with transition metals. All right, so now the second theory is the crystal field theory. So the crystal field theory is fairly simple, and it can explain the magnetism of coordination compounds very well. It can also explain the number of bonds and the shapes of the molecules very well, even though not actually being a bonding theory in itself. And it can also make a good number of statements about the optical properties. So the disadvantage of this theory is that it's not per se a bonding theory because it's based on repulsive interactions. Okay, actually electrostatic repulsive interactions between electrons. So originally it was developed to explain colors in crystals, which are extended solid, hence the name crystal field theory, through the repulsive interaction between transition metal ions in these crystals and the surrounding anions. But later on, it was found it actually also works pretty well for molecular coordination compounds, and hence it has found also applications in coordination chemistry. So we sum up, it's based on electrostatic interactions, but these are repulsive electrostatic interactions, and therefore with repulsive interactions we cannot really explain what holds actually the molecules together, but nonetheless we can explain the number of bonds and the shapes astonishingly well, and we can also explain phenomena like magnetism and optical property in a simple manner. So the last theory is the ligand field theory. So the ligand field theory is actually nothing else but molecular orbital theory applied to coordination chemistry. So this is the most powerful theory. We can explain very well the number of the bonds, the shapes of molecules, the magnetism, as well as also the optical properties in great detail. The disadvantage is that it's the most complicated theory of them all. Okay, so let us look at these three theories in more detail. And let's start out with the valence bond theory for coordination compounds. So let's go through a number of examples and let us assess how well coordination valence bond theory works to explain the properties of these examples. So the first example shall be the octahedral complex hexamine chromium 12+. You see the structure over here. Now let us apply the principles of valence bond theory to this complex. So now first we need to be clear about the electron configuration. So we consider that the metal ligand bond is a dative bond. Okay, so that means that basically we consider the electron lone pair here at the ammonia molecule to be, well, the donor, the electron donor, and the chromium is considered to be a chromium 3+. Okay, that is because this complex here has a 3+ positive charge. Okay, so the amine molecules are being considered neutral because, well, we consider this bond here to be a dative bond, and according to that, the chromium needs to be in the oxidation state +3. So now, what is the electron configuration of chromium 3+? So when you look at a neutral chromium, then you find the chromium in the group 6 in the periodic table of the element. So that means that it must have 6 valence electrons. And remember from our discussion in chapter 1 about atomic structure, chromium has an unusual electron configuration in which all the spins are unpaired. So there are 5 electrons spin up in the 3d orbitals, and there's the 6th one spin up in the 4s orbital. So now what's the electron configuration of a chromium 3+? Well, we need to remove 3 electrons when we want to go from a chromium to a chromium 3+, and that leaves 3 electrons spin up in the 3d orbitals. Okay, so now valence bond theory needs to explain the 6 chromium nitrogen bond. In addition, it needs to explain the octahedral shape. Okay, so now in order to explain 6 bonds, we need to have 6 empty orbitals at the metal, okay, into which the amine ligand can donate its electron lone pair. So now you see you have 1, 2, 3, but with good justification, we can say that the 4p orbitals are also valence orbitals. Okay, because the p orbitals have almost the same energy as the 4s orbitals, they're only slightly higher in energy. So then we have 1, 2, 3, 4, 5, 6 orbitals available. So now, however, there's an additional complication, which is that, well, we could now explain the 6 bonds, but can we still explain the octahedral shape, given that, well, these valence orbitals all have different shapes and they don't all point toward the corners of an octahedron, and they also do not have all the same energy. So how can we, well, make 6 equivalent chromium nitrogen bonds here? So now, like in organic chemistry, valence bond theory uses the concept of orbital hybridization in order to explain shapes satisfactorily. So therefore, valence bond theory now hybridizes these 6 orbitals to make what is called D2sp3 hybridized orbitals. So these hybridized orbitals now have the property that they are all well, equivalent and point into the right directions, namely toward the corners of an octahedron. Okay, so therefore we can now approach our ligands on the corners, 6 corners of the octahedron, make the ligand overlap with the hybridized orbitals to form these 6 equivalent chromium nitrogen bonds. Okay, let's just do this. Okay, so we have here our chromium, and you see now here the 6 hybridized orbitals. So now we orient our ammonia molecules correctly so that they approach the sp2 hybridized orbitals on the bond axes, namely they approach the chromium on the corners, on the vertices of the octahedron. Okay, now that creates orbital overlap, and that creates our octahedral shape. Okay, and the electrons in the amine ligands are now donated into the sp3 dsp2 hybridized orbitals, thereby filling the d2sp3 hybridized orbitals. Okay, so now what's our assessment here? Can valence bond theory explain the number of bonds and the shapes and the shape of this molecule? Well, the answer is overall yes. We can use valence bond theory in a standard fashion without the need to make any unreasonable assumption to explain the 6 bonds and our octahedral shape. So now what about magnetism? Okay, so now what would be the magnetism of our complex according to valence bond theory? Will it be diamagnetic or will it be paramagnetic? Paramagnetic, yeah. And we should be able to measure 3 unpaired electrons in the respective measurements, and that is also experimentally observed. Okay, so therefore, with respect to magnetism, valence bond theory and the experiment is in accordance, and we can say that valence bond theory can correctly predict the magnetism of this complex. Okay, now let's go to another example. Let's go to this tetrahedral complex, tetrahydroxy zinc 2-. So you see this complex here. So this is a tetrahedral complex with 4 dative zinc oxygen bonds. So again, the hydroxide is considered to be a 2-electron donor to a zinc, which now needs to be a zinc 2+ to explain the 2 negative charge here. That is because the 4 hydroxyl ligands have 1 negative charge each. So that's 4 negative charges. So zinc must have a 2+ charge so that we arrive here at 2 negative charges. Okay, so therefore we can form this complex here by the reaction of 4 hydroxides with zinc 2+. Okay, now let's develop our valence bond theory around that. We need to look again at the electron configuration of zinc 2+. So neutral zinc is in the 12th group. So therefore has 12 valence electrons, 10 of them being in the 3d orbitals and 2 of them being in the 4s orbital. So now when we have a zinc 2+, well, we will remove 2 electrons from the 4s orbitals, and having these 10 electrons remaining in the 3d orbitals. So now, in order to explain 4 bonds, we need 4 empty orbitals. We see that right now we have only 1, but with good justification, we can say, well, the 4p orbitals here are also valence orbitals because energetic is just slightly higher. Okay, so now we have our 4 empty orbitals, but like before, the orbitals do not point into the right direction to explain a tetrahedral shape. Okay, and they are unequal in energy in nature, therefore not being able to explain 4 equivalent zinc oxygen bonds. So what do? Well, we hybridize. And in this case, we hybridize the s orbital with the 3p orbitals, and that is known as sp3 hybridization. So we get 4 sp3 hybridized orbitals that now point correctly toward the corners of the tetrahedron here, thereby being able to explain the tetrahedral shape. Okay, because now we can have our zinc with the 4 hybridized orbitals here pointing toward the corners of a tetrahedron, and we can have our hydroxide ligands approach on the bond axis. That means that they approach the corners of our tetrahedron. Okay, we create orbital overlap, and that triggers the donation of the electrons in the electron lone pair here at oxygen into the sp3 hybridized orbitals, which fills the sp3 hybridized orbitals. Okay. So now again, have we explained the number of bonds and have we explained the shape of the complex correctly? Would you say yes or would you say no? You're not sure?
This looks like it explains it okay to me.
Yeah, agreed. So like it's similar to the previous case, right? We just need to hybridize all orbitals, but that's standard procedure in valence bond theory, and that leads to the right number of bonds, and it can also explain the shape. So now what would be the expected magnetism for this complex?
Diamagnetic.
Would be diamagnetic because we have only paired electrons, and that's also experimentally observed. So valence bond theory in this case can also explain the magnetism well. Okay, so far so good. Now let us go to the next example, which is a square planar complex, the tetracyanonickelate 2-. You see the shape here. So now again, we consider the nitrogen carbon bonds here dative bonds. Okay, so therefore we have cyanide anions according to nickel. So these cyanide anions, they have all a 1- charge, so with overall 4 negative charges. you see there's a 2 minus negative charge to the complex. So that makes the nickel a nickel 2 plus. Okay, so that the complex would be formed from 4 cyanide anions coordinating to nickel 2 plus. All right, so now what's the electron configuration of nickel 2 plus? Well, when you have a neutral nickel, then because nickel is in group number 8, we have 8 valence electrons. Okay, so the 4s shell gets filled before the 3d shell, so we have 2 electrons in the 4s, and then the remaining I'm wrong. So nickel is not in group 8, it's group 10, so we have 10 electrons. So 2 of them are in the 4s, and the remaining 8 of them are in the 3d orbits. So now when we have a nickel 2 plus, okay, we remove the 4s orbitals, and we have our 8 remaining d orbitals. Have our 5 d orbitals filled with 8 electrons. Okay, we must have 6 paired electrons and 2 unpaired electrons. Okay. So now you see, we have again 4 empty orbitals available for hybridization, but in this case, we need to explain a square planar shape. It's not a tetrahedral shape. Now, when you hybridize an s and 3p orbitals, you're not getting what you desire because the sp3 hybridized orbitals, well, they point toward the corners of a tetrahedron and not toward the corners of a square plane. Therefore, sp3 hybridization is in this case unsuitable in order to explain the shape. However, if you could hybridize one d orbital, namely the dx square minus y square orbital, with the s orbital and the px and the py orbital, then you could explain a square planar complex in the xy plane, because the respective dsp2 hybridized orbitals then indeed point toward the corners of a square plane. Now, unfortunately, you can't hybridize these because this would require at least one d orbital to be empty. Okay, but you see that's not the case. So therefore, you see now that valence bond theory must make additional assumptions in order to explain the square planar shape correctly. And what it does is, well, it says that we have to reverse the spin of this electron here and move it to the other half-filled orbital, because that frees now that d orbital, and then we have that d orbital available for hybridization. Okay, then we can actually dsp2 hybridize and create hybridized orbitals that correctly point toward the corners of a square. Okay, now the problem with this is that spin reversal is actually quantum mechanically forbidden, and we could criticize valence bond theory for that, saying that this additional assumption that it needs to make is actually not well justified from the principles of, well, quantum mechanics. So, however, if we say, well, for some reason our spin is getting reversed, but we don't know the reason, then we can indeed approach the cyanoligands on the bond axis toward the corners of our square shape, create the orbital overlap, thereby the electron pair gets donated from the donor to the acceptor, filling the d sp2 hybridized orbitals, now explaining the 4 bonds and explaining the square planar shape. Okay, so now according to this approach, would we expect a diamagnetic or a paramagnetic substance? We would expect in this case again a diamagnetic substance, and that's also what's experimentally measured. So we can say that our experimental observation matches what the theory would have predicted. So you see that Valence bond theory can still explain the shape, the magnetism, and the number of the bonds, but with more difficulty. Okay, we must make one additional assumption, which is not a very good assumption to make, actually. All right. Now let's go to 2 more examples. So we also know from experiment that we can have so-called low spin and high spin complexes. So for example, for the electron configuration D5, we know complexes that have 5 unpaired electrons, and well, obviously now the number of unpaired electrons are being maximized, but we also know so-called low spin complexes in which the number of unpaired electrons is minimized. Okay, so now when we have 5, we can actually pair 4 electrons, and then we have only 1 unpaired electron left. So now, how could Valence bond theory explain such a phenomenon? So now let us first look at the D5 low spin complexes. In this case, Valence bond theory assumes a so-called low spin inner orbital complex. So this works the following. We have here our 5 electrons initially being all unpaired. So now what we can do is we again do the spin reversal. Okay. But what you see now is that when you reverse only 1 electron, then that's still not enough. So therefore we must also pair the spin of the other electron. Okay, reverse it, pair. So that leaves us now this 1 unpaired electron left that we experimentally know exists. So now we have 2 d orbitals that are empty, 1 empty s orbital and 3 empty p orbitals. So this is now exactly what we need for D2sp3 hybridization that can explain 6 bonds in an octahedral complex. Okay, so we D2sp3 hybridize, and then our ligands can actually donate their electrons into the D2sp3 hybridized orbitals, and this way we have explained our low spin octahedral complex. So this is called an inner orbital complex because it only uses inner orbital, in contrast to what we discuss now, a so-called outer orbital complex. And we will need a so-called outer orbital complex in order to explain, well, the high spin complex. So because we experimentally know we have a high spin complex with 5 unpaired electrons, we cannot, like previously, pair our spins, as questionable as this may be. It's just wouldn't match or explain the experimental observation. So what else could we do? Well, in order to D2sp3 hybridize, we would need 2 additional d orbitals. So where could we find them? Well, we could just make an additional assumption and say, well, there are well, the 4d orbitals also available for bonding. However, this assumption is being questionable because it's actually known that the 4d orbitals are significantly higher in energy than the 4p and the 4s. Therefore, it's questionable to assume that they're valence orbital, and therefore it's questionable to assume that they're actually involved in the bonding. Okay, but if you make this questionable assumption, then we actually do have two additional d orbitals available. We can d2 sp3 hybridize. Okay, then we actually leave our 5 electrons here unpaired as we need to do it. We have these hybridized orbitals available for bonding, and that leaves, well, 3 4d orbitals left over. Okay, so as we form the bond, we again donate electrons, in this case 12 electrons, from the 6 donors into the d2 sp3 hybridized orbitals, and that will explain our 6 bonds in the octahedral shape. Okay, now low and high spin complexes are not only known for the d5 electron configuration, they're also known for other electron configuration, for example d7, and then things become even more complicated for valence bond theory. So let us first consider an octahedral d7 low spin complex. So you see that, well, we have 7 electrons in the 3d orbitals. Now we need to maximize the spin pairing, and that means that to explain a so-called low spin complex, that means again we need to reverse the spin of one electron and pair it with the spin of another one. Now you see that frees only one d orbital. In this case, however, we could not, well, free the other d orbital that we need by doing more spin pairing, because there are no electrons available that could be spin paired. So what do we do then? Well, we say we just assume again that the 4d orbitals are available as well, and then we just move the 3d electron into the 4d orbital, which is of course, well, an assumption which somewhat lacks justification, because this orbital here has a much lower energy than this orbital over there, but nonetheless we could this way free the 2 d orbitals from electrons, so we would have 2 empty d orbitals available that we could hybridize with the 4s and 3 4p. So that gives then d2 sp3 hybridized orbitals, and they then could be filled by the donation of electron pairs from the ligands into the hybridized orbitals. Okay, so this way we could explain the low spin complex, which is only one unpaired electron. But now what about the high spin complex? So in a high spin complex, the number of unpaired electrons are being maximized. So that's already the case here. So how do we get 2 empty d orbitals? So now in this case, we again assume that the 4d orbitals are available, and we now take again the outer orbitals for hybridization, because we must. Okay, and now we just hybridize these, and that leaves the 3 4d orbitals here again empty, and the electrons are getting filled into the d2 sp3 hybridized orbitals. Okay, so now what you can see from that is that we basically make assumptions as we please in order to explain shapes and the number of bonds and the magnetism. Okay, without really explaining what justifies these assumptions. Therefore, overall, the conclusion is that valence bond theory has limited utility for coordination chemistry. So while it's extremely useful in organic chemistry, in main group chemistry, it has limited utility for coordination compounds. But I think it's nonetheless valuable to look at this because it also shows, well, the limitation of a concept and the limitations of a theory for a particular field, in this case, coordination chemistry. All right, then this was the part about valence bond theory. I see we actually have a few more minutes time. And therefore, we can start with the crystal field theory already. Just browse this here. So now, like I said previously, the crystal field theory is based on repulsive electrostatic interactions that create a crystal field of a particular shape around a metal ion. Okay, so now let us first look at the hypothetical case of a spherical crystal field. Okay, so in a spherical crystal field, we assume that we have, well, an electrostatic field produced by electron that surrounds the metal in a spherical way. So now let us think about what will happen to the energy of the metal orbitals. Okay, so now you can say that, well, without a field, our 5 metal d orbitals had a certain energy. And now, because of that negatively charged spherical electrostatic field around the metal, there is, well, repulsion between the negative charges of the field and, well, the negative charges of the electrons in our d orbitals, and therefore the energy of the orbitals is being raised. Now, because the electric field is completely isotropic due to its spherical nature, the energy of all the 5 d orbitals is increased by exactly the same amount. So that spherical crystal field is, of course, not a realistic situation in a coordination compound, because we never have spherical complexes in which ligands surround a metal ion in a spherical way. Okay, but we can, of course, observe complexes in which ligands surround the metal, for instance, in an octahedral way. And in this case, we would have what is called an octahedral crystal field. Okay, So these ligands would contain electrons, and these electrons would be associated with an electric field, again, which would produce now electrostatic repulsions between the electric field and the electrons in the metal d orbitals. So same principle, but because an octahedron is not completely isotropic, now certain orbitals are increased in energy more than others. Okay, so now which ones are increased more and which ones are increased to a smaller degree? So now we define the coordination system so that our ligands, our 6 ligands producing the field, lie on the bond axes. Okay, that has now the consequence that the dz square orbital and the dx square minus y square orbital, which have both most electron density on the axes, are now repelled more strongly by the octahedral ligand field in comparison to the other 3. The dxy, the dxz, and the dyz, which have electron density in between the axes. You can see this here. Okay, so therefore, relative to the spherical crystal field, the energy of these 2 orbitals is increased, while the energy of these 3 orbitals is decreased. Okay, note though that also the energy of the dxy, the dyz, and the dxz is increased relative to no field. Okay, because there's still some repulsion ongoing. All right, now you see that the dx square minus y square and the dz square orbital, they have quite different shapes. Okay, but still the energy is increased by exactly the same amount. How can we explain this? We can explain this from the standpoint of symmetry. Okay, we know that the dx square minus y square and the dz square orbital are degenerated in the octahedral point group OH, and an symmetric degeneration also implies an energetic degeneration, which explains why the x square minus y square and the dz square orbitals have the same energy. Because they have the same symmetry, they are called also the EG orbitals. Now, for the same reason, the energy of the dxy and the dxz and the dyz orbitals are decreased by exactly the same amount, and the energies are degenerate. In the point group OH, these orbitals are triply degenerate and have T2G symmetry. Therefore, we call these 3 orbitals also the T2G orbitals. So now the energy difference between these 3 and these 2 are called the delta O, and that delta O represents the octahedral crystal field strength. Okay, so the larger the delta O, the larger the respective crystal field, which is produced by the ligands surrounding the metal ion. So now, because of energy conservation arguments, the dxz, the dyz, and the dyxy orbitals are decreased by 2/5 of delta O, and the 2 dz square and dx square minus y square orbitals are increased by 3/5 delta O. Okay, so this is the octahedral crystal field. Of course, we have other crystal fields, such as, for instance, the tetrahedral crystal field or the square planar crystal field. But I see that we are at the end of our time. Therefore, let us stop. at this point,